So let's continue with our Bayesian learning approximation. So as you saw, the prior probability, big P of HI, is very important for both map and Bayesian learning. And to avoid overfitting, so overfitting happens essentially when the hypothesis space is too expressive. That is, when it contains many hypotheses that fit the data set well. So to avoid overfitting, Bayesian and map learning use the prior probability to penalize complex hypotheses. So the more complex a hypothesis, the lower its prior probability, because there are so many of them. On the other hand, more complex hypotheses have a greater capacity to fit the data, obviously. In the extreme case, a lookup table can reproduce the data exactly. So the hypothesis prior then represents a trade-off between the complexity of a hypothesis and its degree of fit to the data. So the prior penalizes hypotheses that are too complicated. You can think of, for example, trying to fit a polynomial to 5 data points. You can obviously use a fifth degree polynomial and have a polynomial that passes by every single data point. Obviously here you overfitted your data, and in that case, in Bayesian learning, we will see that the prior probability for this hypothesis will be very low. So we can see the effect of this trade-off between complexity and degree of fit mostly in logical cases where the hypothesis space contains only deterministic hypotheses. Okay, like the example we just did with the candies. For example, H1 says that every candy is cherry. In that case, the probability of the data given the hypothesis is 1 if the data is consistent, if the hypothesis is consistent with the data we observed, and it's 0 otherwise. So we can see that H maps then will be the simplest consistent hypothesis. Okay, that is consistent with the data, obviously. Okay, therefore, map will provide a natural reflection of Occam's razors, which is essentially if multiple explanations are available for a given situation, we always go with the simplest one. So map in that case, you will see that automatically is going to take the simplest one of all the hypotheses. I mean, you can see that mathematically if you take the log of the equation here, and so you can see here in log form. So essentially, you can see that to get the minimum description length MDL, that we will take the lowest prior probability. So even when the data set is large, the prior distribution over hypotheses then becomes less important. So as you observe more and more candies, you can think of this graph right here, where you started really, which is at 0 candies observed, becomes irrelevant, okay, because you will quickly converge to the correct solution. Why? Because as you collect more data, the evidence from the data is strong enough to swamp the prior distribution over the hypotheses. So that means that maximum likelihood learning is a good approximation to Bayesian and map learning with large data set, but it has problems with small data set. So if we have a large data set, then we can just take the hypothesis with the maximum likelihood and make prediction based on this hypothesis. But if we have a small data set, that becomes a problem. Okay, so maximum likelihood, then we choose the hypothesis that maximizes the probability, the likelihood function, which is the probability that we observe the data given a specific hypothesis. And this is the standard non-Bayesian statistical learning method. Okay, so when you're using a linear regression or anything like that, what you're doing is you're using maximum likelihood learning. Now, let's see now how we can do maximum likelihood parameter learning for a discrete model. So we're going to shift now to what's called learning with complete data. So the general task of learning a probability model given data that are assumed to be generated from that model is called density estimation. So density estimation essentially is a form of unsupervised learning. And the simplest case of that is when you have complete data. So data is defined as complete when each data point contains values for every variable in the probability model being learned. So everything is observed essentially. So we focus on parameter learning, which is finding the numerical parameter of the probability distribution whose structure is fixed. So we assume, for example, that our data has been generated by a binomial process following a beta distribution, and our goal, for example, is to find the parameter of this beta distribution. So the simplest example of that is what we call, let's start with discrete models. So probability distribution with discrete parameters, like the beta distribution. So to introduce this, suppose that we buy a bag of lime and cherry candy from a different manufacturer. And that manufacturers, we don't have any prior information about the proportion of cherry and lime candies. So essentially the fraction of cherry candy could be anywhere from 0 to 1. So that's essentially our unknown parameter. So in that case, we have a continuum of hypotheses, right? We have an infinite number of possible value for the proportion of cherry, theta. So that gives us an infinite number of hypotheses. The parameter in this case, which we call theta, is the proportion of cherry candies. And each hypothesis will be referred to as h sub theta, okay, for a given value of theta. Now, if we assume that all proportions are equally likely a priori, so our prior probability is the same for all of them, we have no clue what is the true value of theta, then a maximum likelihood approach makes sense here, right? We want the value of theta that maximizes the likelihood to observe the data we're observing as we start opening candies. So if we model the situation with a Bayesian network, we just need one random variable, which is flavor. Okay, so essentially this random variable has two possible values, could be cherry or could be lime. Okay, and the probability of cherry is theta. Now suppose we unwrap n candies, of which we find C candies are cherry, okay, and n minus C are L candies, for example, lime. So the likelihood in that case is going to be given by this equation, which is theta to the power C, because we found C cherries, right? So theta to the power C. So this is the probability that we observe this data times the number of lines, which is L, 1 minus theta to the power L. Okay, so these are all, of course, we assume here independent, identically distributed observations. So when you pick one candy, it does not impact the probability that you pick the next candy and so on. Okay. Now, if we want to find the maximum likelihood, we want to maximize this equation right there. Now, because this is a product, we don't really know how to maximize the product. So we're gonna take the log instead, because that makes it an addition instead of a multiplication, which gives us the equation you see here, which is C log theta plus L. This is an L. Sorry for the formatting here. Log 1 minus theta. Okay, and so this is the log likelihood, and now we want to maximize relative to theta, so we want to find the value of theta that maximizes this likelihood log likelihood function. So we're going to take the derivative of this equation with relative to theta. So the derivative of the log theta is 1 over theta, and derivative of log 1 minus theta is 1 over 1 minus theta. So we end up with this equation, which is essentially theta is equal to the number of cherries you picked divided by the total number of candies that you opened so far. That kind of makes sense. So if you open 10 candies and you found 7 of them were cherries, so your best guess is the proportion of cherries is 7 over 10, which is 0.7. Obviously, that doesn't work if you haven't picked any cherries yet, because you would have division by 0. So the maximum likelihood hypothesis then tells us that the actual proportion of cherry candies in the bag is equal to the observed proportion in the candies we unwrapped so far. So it seems that we've done a lot of mathematical work here and ended up with the obvious, right? Because essentially we could have guessed that without doing any analysis. But by doing that, we defined a method essentially, okay, in a 3-step process to find the maximum likelihood hypothesis. So that's 3-step process. Let's recap what we did. The first step is to write down an expression for the likelihood of the data as a function of the parameters, one or more parameter, which is this equation right here. So write down this expression for the likelihood. This will depend, of course, on the probability distribution that you're using and the process that you're modeling. Second step, take the derivative of this likelihood with respect to each parameter. So in this case, we only have one parameter, but in general, we could have many, many parameters. And then finally, find the value of the parameter that makes the derivative equal to 0. Okay, because that will give us the maximum value of derivative. That's essentially going to be the same 3 steps we're going to follow from now till the end of this class to train neural network and train much more advanced methods. We're just going to follow these 3 steps, like write the likelihood function, take the derivative of the likelihood function, solve for the unknown parameters. Now, each one of these steps is going to be more complicated as the models get more complicated. Okay, let's continue in the next.